general relativity, step by step. I'm trying to work out the relative acceleration of two closely separated bodies, and I'm using effectively a Taylor transform that should be evaluated at point x to calculate the relative acceleration, which is this thing here. Okay, well, let's just carry on. Let's just substitute one into the other and see what we get. It's just minus di phi by di xi evaluated at x, this term here, minus nk di 2 phi by di xk di xi evaluated at point x, which is this term here, minus di phi di xi evaluated at x, which is this term here. We're subtracting a negative. So, haha, things start to cancel, which is quite nice. That cancels out with that. I live for that moment when things cancel out. I love it. I love it to bits. So what does that tell us? That tells us that relative acceleration, which is d2 by dt squared of xi minus ni, minus xi, minus d2 xi by dt squared equals, what's my sign? Have I got lost a sign? No, I haven't. It's minus nk di 2 phi by di xk di xi evaluated at point x. So that's quite nice. Right, my computer glitched out there, so I'm going to have to remember where I am. d2 by dt squared xi plus ni. So this is the acceleration of xi plus ni minus d2 xi by dt squared. Xi, or x, the vector, I guess, equals xi, is a function of time for a freely falling particle. And we know that the difference between x, so we've got the freely falling particle here, we've got another particle here which is also freely falling at separation n, and the relative acceleration, because we're subtracting out the acceleration of x, is equal to minus nk di 2 phi by di xk, summed over k of course, di xi evaluated at position x. And so if we've got lots of different particles here separated by lots of different n's, so that might be n1, this particle here is n2, this is n3, the whole thing might be accelerating in this particular direction, but because we're considering the difference between xi and these other little particles here, we're just considering relative acceleration, which is given by this formula here. So even though the whole thing's accelerating downwards, we can fall with it effectively, and we can look at what happens to the test particles close to our main particle x here. And what generally tends to happen is that if the whole thing's accelerating in a sort of vertical direction here, we just put four little particles here. These ones, if I just switch to green it might be easier, these ones tend to accelerate in towards, and these ones tend to accelerate outwards like that. So what that means is that a little shell, a little sphere of test particles will become stretched and squashed as it falls down. And of course, these are known as tidal accelerations. This is a tidal force. Okay, so that's what's going on here. So we've got lots of different particles relative to our standard particle, and they've got accelerations either towards or away from our reference particle, depending on which orientation they're in. And that represents tidal acceleration. And I'm going to stop there. Stop.